Okay, Googlies, Grubbers, Lollies. How Cricket helped us improve our throughput by 200%. Okay, we're talking about cricket, the sport, not the animal. Googlies, Grubbers, and Lollies are three slang words from cricket that have nothing to do with this talk. They're just funny sounding cricket words. If you want to know what they mean, you can look them up online. But cricket is very relevant to this talk, and soon I'll tell you why. My name is Ethan Pransky, and I'm a software engineer at AppsFlyer. I've been at AppsFlyer for about 2 years, and thank you. And I'm in a team called Partner Development Solutions, and our responsibility in Partner Development Solutions is for all the outbound communication that AppsFlyer handles. And what is AppsFlyer? AppsFlyer is a mobile attribution and analytics platform that helps our clients, app marketeers, optimize their user acquisition funnel. And the way that this works is that we have an SDK which our clients integrate in their applications. And our application can be found in about 99% of devices worldwide. And basically the way that our solution works is that that SDK fires events to our web servers whenever an event happens inside one of our clients' applications. And that sums up to about 60 billion incoming events every day that we receive in our web servers. And in PDS, we end up sending about the same amount in outbound communication. Outbound communication, I mean, we send HTTP requests, which we call postbacks. So we also send about 60 billion postbacks every day and peaks of 1 million postbacks per second. Okay, so why are we here? So over the past few years, we've grown a lot, okay? And a little over a year ago, we were handling just about a third of the traffic that we're handling today, so about 20 billion events. And so that means that over this time, we've had to learn how to scale both quickly and efficiently. And as developers, we don't want to spend our time doing performance optimization. A lot of people say don't do performance optimization at all, only do it when it's absolutely necessary. As developers, we're paid to build features and fix bugs, right? So I want to tell you about a story that happened to us about a year ago when we were forced to handle a massive increase in incoming events and how we scaled up to handle those incoming events. And from this experience, how we generated a simple and easy framework or methodology for scale adaptation and performance optimization, which doesn't break your development cycle and is based on first order principles. And I think this methodology is applicable to any sort of application and any sort of organization. Okay, so I told you I would tell you why cricket is relevant to this talk. And cricket is relevant to this talk because at AppsFlyer, over the past year, we've become huge cricket fans. Okay, and this guy's name is Rohit Sharma, and he's the captain of the Mumbai Indians Indian Premier League cricket team. And he's huge in India. Okay? And you might be wondering, why is an Israeli R&D organization so obsessed with cricket? Well, a year ago, this happened. The first game of the 2018 Indian Premier League cricket season, and it featured the Mumbai Indians, our favorite team, facing off against their rival, the Chennai Super Kings. The Mumbai Indians were the reigning champions, and the Chennai Super Kings were our fierce competitor. And everybody in India was watching this game, including tens of millions of people on their mobile devices. And it just so happened that one of our clients, Hotstar, had just secured the exclusive rights to stream all Indian Premier League games for the 2018 and beyond. And as you can imagine, those 10 million users, those 10 million Indian fans started bombarding our servers with events. And overnight, we started experiencing an over 50% increase in incoming events. So instead of handling 20 billion events per day, we were handling 40 billion events per day and more. And this continued day in and day out as the season continued. And we were struggling to manage, especially in partner development solutions, we were struggling to manage. And I'll tell you a little bit about what we do in partner development solutions so you get a better idea. Basically, we have three main services that we handle in PDS. We have a service which is a rule engine, which given an incoming event from our SDK and a client configuration, decides to whom we send postbacks and what those postbacks contain. It passes that information on to a service we call the Tentacle. And the Tentacle's job is to do the actual network I/O, to send the HTTP request, receive the response, And then it passes that response on to a third service, which is a post-processing service, which logs to databases or decides to do retries, whatever is necessary to do with the response. And what I mean when I said that we were struggling to handle this expressed itself in the fact that the tentacle was building up a lot of what's called consumer lag. And by consumer lag, it's because all three of these services communicate with one another using Kafka, okay? And what consumer lag is the difference between the offset that you've successfully consumed from in a topic and the highest offset in that topic. And basically, you can scale up. What's great about Kafka is that you can have as many parallel consumers as you want on a topic, but it has to be pre-configured. And you can have as many parallel consumers as there are what's called partitions on the topic. So the first thing we did is we tried scaling up the amount of instances that were running the tentacle. The tentacle runs, by the way, each one runs in a Docker on its own machine. So we tried to scale up the amount of instances of the tentacle to the maximum amount of partitions allowed, but we still weren't keeping up with the traffic. And so the only other thing that we could do at this point is we could try to upgrade the instance types that we were using to more powerful machines with more cores. But when we did this actually didn't work either. We still had these lags building up, and we weren't keeping up with the incoming traffic. And this is really problematic because our clients depend on this outbound communication in order to make real-time business decisions. Okay, and they even do billing based on this. So it's really important that we meet an SLA that our clients are expecting of near real time. So we had this lag, we couldn't let this happen. So eventually we could reconfigure our Kafka topics so that we could allow more partitions, allow more instances of the tentacle to consume, and we met the demand. But this was really problematic because it showed that we didn't have elasticity, right? It showed that even when we upgraded our machines, we didn't know how to take advantage of those machines in order to overcome the incoming traffic. And reconfiguring your Kafka topics and your configurations is kind of a slow and arduous process, and it's not the type of thing that you would consider elastic. So we're looking for a solution and trying to figure out what was happening. And then a colleague of mine came to me. I like to think of this colleague as the Jesus because nobody fucks with him. And he said that you really should be thinking about this problem and elasticity in general in terms of what queuing theory has to tell us. Okay? And he said more specifically you should be thinking about it in terms of this idea from queuing theory called Little's Law. And Little's Law, as I said, is an idea from queuing theory, which was developed in the field of operations research, so optimizing factories and supply chains, etc. And basically what it says is this. It says that given a system, the number of units in a system will be equal to the arrival rate of units to the system times the time spent of a unit in that system. Hope that made sense. I'll get into it more in a little bit. And the more that we started using this and started applying to our systems, we actually realized that this law is not just is universally applicable, and it actually can be applied to any sort of application and any level of application. And it's so applicable that in order to remind us of ourselves of this, is that we developed this sort of mantra that we call everything is little. Okay? And that's to remind us that it can be applicable everywhere, but it also has a few double meanings. And the double meanings are that in and itself is a very little equation. And it takes very little to conceptualize this law. It's really simple. And it helps us, and the power of it is that it helps us break our large-scale systems into little problems that are easy to diagnose and solve. This is John Little, by the way. He proved this law. He's still alive. And he's a professor at MIT. Anyway, so I'll define these variables. I rewrote it so it's a little bit more applicable for software development, for our realm. And the way I like to define it is this, that C, our capacity, so the amount of events in our applications at a given time, is equal to our throughput, which is the exit rate of events from our applications, times the latency of events in our application. So latency is the amount of time that an event spends in our application. And I'll define one more variable, which is arrival rate, which if throughput is the rate at which events exit our system, arrival rate is the rate at which events enter our system. And so how can we start applying this? Well, at a high level, we said that our problematic system, our application, is the tentacle, right? and the tentacle was consuming from Kafka, okay? So how can we model this relationship using Little's law? Let's take an example to understand this relationship a little bit better. So this is Wankhede Stadium. This is where the Mumbai Indians play their home games. And the scenario is that we have a bunch of excited Mumbai Indian fans arriving to Wankhede Stadium. And they're arriving at about 200 fans per minute. And there are ticket stands that are spread outside the stadium. And it takes each fan about a minute to pick up his or her ticket. And they said there's 100 stands around the stadium. Okay, so let's play this scenario out for a second. What happens in the first minute? 200 fans arrive, 100 fans go into the ticket booth, 100 fans go into the queue. After the second minute, the 100 fans from in the ticket booth leave, and 100 fans from the queue go into the ticket booth, and we have 200 new fans in the queue, so now 200 fans in the queue. After the third minute, 100 fans again leave the ticket booths, 100 fans from the queue, another 200 into the queue, now we have 300 fans in the queue. After 4 minutes, we have 400 fans in the queue. And what we can see is that Little's law holds up, right? So we have 100 fans as our capacity, our latency is 1 minute, and we can see that always, every minute, we have 100 fans leaving. So our throughput is actually 100 fans per minute. This is, and if it wasn't clear, the ticket booths here represent the tentacle, and the queue here represents Kafka, right? And what's cool about this is that, not that we can just think about this system as a whole in terms of Little's law, but we can actually think of the ticket booth area and the queuing area each as their own subsystems and apply Little's law to each one of them. So we saw what happened in the ticket booth. We said that it has a throughput of 100 fans per minute. But what's happening in the queue? Well, the queue, if you think about it, it has a throughput also of 100 fans per minute. It doesn't have any logic of its own. It inherits the throughput of the ticket booths, right? And what's the capacity of the queuing area? Well, it's just the size of the queue, right? So if we rewrite Little's law, we can understand that we can figure out what the latency will be at any given time for the queue, okay? And just as an aside, a lot of people think that when they're using queue in their systems that they can make some voodoo increasing or decreasing the size of their queue and that'll help their throughput. But this proves that it doesn't, right? Because if we just limit the size that a queue can be, it'll also limit the latency of that queue, right? And if we don't limit the size of that queue, we can see that it'll just grow endlessly and endlessly, right? So the capacity will keep growing and growing and growing, and it'll approach infinity. And since the capacity will approach infinity, also the latency of the queue will also approach infinity. And so that shows us that from a fan's perspective, even though the system as a whole always has a throughput of 100 fans per minute, from the experience of the fan, it'll be the sum of the latency of the queue and of the latency of the ticketing error, which is also infinity, okay? And this tells us something profound that queuing theory tells us, which is that whenever we have an arrival rate which is greater than the throughput of our system, the latency of that system will always strive to approach infinity, okay? And so that means that our goal is always to increase our throughput to at least the level of our arrival rate in order to reach a stable system. And so how do we do this? Well, if we rewrite Little's law again, we can see that we only have two levers for affecting throughput, right? We can either increase capacity or decrease latency. That's it, okay? And if we take this into the realm of software development again, if we think about latency, well, what's latency in terms of software development? It's doing the same task but in less time, okay? And that means better algorithms or otherwise touching your code, which in general is something we want to try to avoid, right? Because we don't want to break our development cycle. We don't want to spend time doing performance optimization. So when we're thinking about doing scale optimization, we want to look towards capacity increase, because capacity increase, well, it might not be free, it's easier, right? You're usually touching configurations. In fact, in the example with the Kafka and the tentacle, we just had to increase the instances. We didn't actually have to make any merge requests. We didn't have to commit code or otherwise. All we had to do is increase the amount of instances. So it was relatively easy, right? So the rule of thumb is let's look towards capacity increase before we look at latency decrease. So we can actually break down this relationship between Kafka and the tentacle a little bit more, because what's actually a Kafka topic? It's a set of partitions, and each partition is its own queue. And we can look at the relationship between a Kafka partition and each of the instances and break down the instances themselves into their own subsystems, right? And if we do that, we can see in the tentacle, we basically had 3 subsystems, if we break it down. We have a consumer subsystem, which its queue is Kafka, and it's a thread that all it does is take from Kafka and puts into another queue, which is our sender subsystem, which that does the actual I/O, receives a response, and then puts in the producer queue, and the producer subsystem just produces the Kafka. That's all the service does. Okay? So this is a little bit different from the example before, because now we have multiple subsystems. We don't just have a single subsystem, a single system. So we need to understand how multiple subsystems work and get an intuition for that. So we can expand our example from before. And this time, we see that we always had a throughput of 100 fans per minute leaving our ticket booths, but now this is a subsystem of a system as a whole. And that 100 fans per minute throughput now determines the arrival rate of our next station, which is a security check. And in the security check, we have 250 stations, and it also takes 1 minute to process them. Okay? And so the potential throughput of the security system is 250 fans per minute, but in actuality, it'll only have a throughput of 100 fans per minute, because that's the arrival rate, right? So this tells us something profound that queuing theory tells us about when we have multiple subsystems, which is that when we have multiple subsystems, the throughput of our system as a whole will only be as good as the lowest throughput of our subsystems. And it also shows that if we misallocate our resources, that we can cause for ourselves suboptimal throughput, right? Because if you see here, if we could just move 100 of those security checkers over to the tickets, then we could gain the throughput that we need. We'd have an efficiently running system. So now with all this in mind, we can think about this like we all think about this. We can think about this like bottlenecks, right? We're all familiar with bottlenecks. But now we can define what a bottleneck is. A bottleneck is whenever we have is the subsystem within a system which has the lowest throughput, okay? And we have the tools to fix that throughput. We either increase capacity or decrease latency. And we can keep doing this. We can keep increasing the throughput of our subsystems until we reach the maximum capacity of our system as a whole, which when we're talking about software, that's defined by our machine, right? So our CPU, our memory, and our disk. That's it. So we can go through this exercise until we reach the maximum of those resources. And so when we looked at our tentacle instances, this ended up giving us a hint at what was going wrong. Because when we looked at our tentacle instances, we saw that the machines, after we upgraded them, were only using 30 to 50% of the CPU that each machine had allocated to it. So we had some work we could do. So how do we go about debugging it? Well, this is what was happening in the tentacle. When we were reaching peak times, our 2 internal queues were all filling up. We knew what was happening in Kafka, a lag was building up, okay? So we had some bottlenecks we need to work out. So what do? We want to add capacity. In software development, we add capacity by adding concurrency. Okay, so in our producer subsystem, we could add another producer thread. There was no reason why we couldn't run more than one, taking from that queue. And when we did that, that worked. Little's law held up, and we got the throughput that we needed to clear up that queue. So then we thought, let's do the same thing for the sender subsystem. We still had a bottleneck. And actually, when we did that, it didn't work. Okay, so this is kind of confusing because adding capacity should work, right? Well, we were trying to figure out what was happening here, and then we started to get a hint once we generated for ourselves flame graphs. And so we generated flame graphs. For those of you who don't know, they're a profiling tool made by Brendan Gregg at Netflix, and they help tell us which functions in our applications are using the most CPU. Okay, and a flame graph looks like this. And on the x-axis of a flame graph, it shows you the time on CPU per function. And the y-axis shows us the call stack of those functions. And so what immediately jumped out to us here was this stack here, right? You probably can't see it, but what it's showing is that what was using a lot of CPU here was a third-party library called HTTP-Kit. We write all our services in Clojure, by the way. And this is a Clojure library that we were using. And this is the library that we were using to actually send the HTTP requests. Okay, and why was this weird to us? Well, we were thinking, well, this library only does I/O, and I/O shouldn't really be using a lot of CPU, especially it's using non-blocking I/O, and non-blocking I/O uses can use a single thread to manage multiple connections. So it shouldn't be using a lot of CPU, right? When we zoomed in, we could see, yeah, the I/O wasn't using a lot of CPU. But what was using a lot of CPU was SSL. Okay, so encrypting and decrypting our messages. Most of our clients and our partner networks, they want to encrypt their messages. So this is what was actually, this was causing a lot of CPU. And why did this? And so this started to give us a hint at what we were missing here, because something was happening in HTTP-Kit that we weren't taking into consideration. So we started digging into the source code of HTTP-Kit, and this is what we found, is that inside HTTP-Kit there's this internal class called HTTP client. And when we call the request function of HTTP-Kit, what does it do? It creates a request object, and it submits it to this internal queue of HTTP client. And then there's another internal thread within HTTP client that takes those requests, and it manages the state of each request. So connect, write, read. And this is where the SSL is happening, it turns out. And then when it's done, it submits the response to a thread pool executor, which is just another queue and another set of threads. And that's what executes our asynchronous callback of our HTTP request. Okay, so what do we have here? We had more subsystems hiding in HTTP-Kit that we weren't taking into account. And so now, with this in mind, we could actually take these subsystems, flatten them into our diagram from before, and it looked like this. And after adding some metrics here, we could see that that internal queue in HTTP client was building up all the time. So that means that there was a bottleneck happening there. And that made sense because we saw SSL was taking a lot of CPU. And we saw that actually we were limiting the amount of in-flight requests that we could have at a given time. And what was happening, that was causing back pressure, which was causing the sender queue to build up. Okay? So we know what to do with bottlenecks. We need to add capacity if we can. We still had more CPU we could use. We hadn't reached max capacity, so we did a minor tweak. We added another HTTP client, and that ended up being the solution. Okay? So that cleared up all of our queues. We had an officially running system, and they only started filling up once we reached maximum CPU. And so this was great because this resulted in a 2 to 3 times throughput that each machine could do, that each instance of the tentacle could handle. And we were rewarded by these efforts by being able to run with 1/2 to 1/3 the machines that we were running before. Okay? And what was especially great about this is that we didn't have to break our development cycle in order to do any of this. All the analysis that we did was all offline, and the touch and everything we had to do in code was basically handled using touching configurations. There was some minor code touches, but basically we didn't affect our business logic much at all. And so this was a great result. But the point of this talk is not to talk about this specific story, but rather to talk about the methodology, because that's the important takeaway. Because what do we do here? We kind of generated for ourselves a recipe about how we can approach scale optimization in general. And the recipe looks like this. You break your system into your lowest level subsystems. You flatten them out. You find the lowest throughput of your subsystems. You solve that by increasing capacity or decreasing latency. And you repeat this until you reach the maximum capacity that your machine has to offer. And that's it. And I think that this is kind of like a simplified example, right? This is just a data pipeline. Like it was really easy to visualize everything. But actually, this recipe is generic enough that you can apply it to any type of application and any type of organization. Because no matter what type of application, whether you're talking about web servers or databases or any sort of data structure or abstraction can be modeled using Little's law, right? Because you always have a latency and a throughput. So the power of all of this is not necessarily what we were able to do with it, but actually how we're able to think about our systems as a whole and actually how we're able to model them. But there's another important lesson here, and the important lesson here is that this is Milton Friedman. He's a Nobel Prize-winning economist. He's not alive anymore. And he wrote a book that's called "There's No Such Thing as a Free Lunch." And I say this because the solution in the tentacle ended up being when we stopped just looking at the code that we wrote and we're looking at our dependencies. So we're looking at other things that were happening in our machines besides just the code that we wrote. And so this is important because while everything can be modeled using Little's law, we still need to understand everything that's happening in our machine. So it's not just dependencies, but can also be things like garbage collection or other processes running on your machine. It can all be modeled, but we have to understand it all. Okay, so to sum everything up, the 2018 season, cricket season, ended great for AppsFlyer. We were able to save a lot of money and run using half the machines that we were using before, or a third of the machines even. And we were able to use the lessons that we gained in this mantra, everything is little, to gain elasticity in a lot of our services. And we've used these techniques throughout the last year through international cricket play and Black Friday and Chinese Singles Day and all these events that cause us these massive spikes in traffic. We were able to gain the elasticity we need, and we did this all by thinking of everything in terms of what Little's Law has to show us. Unfortunately, though, the 2018 season didn't end well for the Mumbai Indians. They only finished in 5th place. They didn't even make the playoffs. Very disappointing for all of us at AppsFlyer. We were sad. But fortunately, in 2019, they took the championship for the 4th time, beating their rivals, the Chennai Super Kings, in a thriller, which was not only exciting to watch, but it broke a record worldwide for most simultaneous live streams. And as you can imagine, that also broke some records at AppsFlyer. We had some massive spikes that day. But I'm happy to report that because of our efforts here and because of the way we're able to structure our systems, because of Little's Law, that we were able to handle this easily. Now currently, as we speak, the Cricket World Cup is happening. And right now, as we speak, India is facing off against Pakistan. And so I should probably finish this lecture and go check our dashboards. And I also want to check the score. So to sum everything up, let's just sum it up like this. Go India.